Okay. So, good morning. And welcome. Welcome back to the course. Before, although the program says we should start talking about agricultural remote sensing, now I would like to briefly, really only briefly touch on a topic that I announced but was unable to complete yesterday, which is about hyperspectral remote sensing. Because this is a specific type of data which has, I mean, itself as a type of data has been around for a long time now, but there has never been large, wide availability of such data. And it has a great potential because it contains a lot of spectral information, and it is on the verge of becoming mainstream because there's a number of hyperspectral satellite missions that are coming up, including one from Sentinel, from the Copernicus initiative. So just a few points to give you a flavor of what these data are and how you can tackle the issue of extracting information from these data. So in a sense, if I get back to the original scheme that you may remember from one of the early lectures, I'm not aiming at any specific point, but I'm considering the whole processing chain and how it changes when you switch from multispectral to hyperspectral data. I want to point out that I'm still talking about optical data. Okay, so we are still in the so-called optical window. What changes here is just the way you break down the spectral information, the way you break down the spectral response of the object that you're looking at. And as we will see, this, which at first sight seems just a technical difference, actually it makes a difference also in terms of how you handle the information. Okay, so hyperspectral remote sensing is the space companion, if I can say so. It's a space children, if you will, the space child of a much older discipline, which is called imaging spectroscopy, which has been around for decades, if not for centuries, but for decades for sure, which consists of analyzing matter in laboratory by, for example, bringing it to high temperature and looking at the spectrum of the emitted radiation. Okay, it was discovered that by looking at how this radiation is distributed along the spectrum and how basically atomic and molecular resonances act on it and absorb the radiation that was supposed to be emitted, but it is not. Okay, this creates a situation similar to the one that I described at the beginning of the course with the keys that you may remember. Okay, so this was done in a lab environment, okay, in a very clean and very favorable lab environment. Now, when you move from this situation to hyperspectral remote sensing, you're moving to a much more challenging situation where you try to do the same, but with a lot of noise, a lot of disturbing factors involved. So, whereas in a lab environment, you can sense the response and then, for example, compare the absorption, called absorption lines with a standard set of absorption lines. When you move to remote sensing, we are basically, what you are doing in hyperspectral remote sensing is, technically speaking, it is breaking down the spectral response in much smaller chunks. To give you an idea, a technical idea, when we work with multispectral remote sensing, we can safely assume that each band takes more or less 100 nanometers. Just as a figure of reference, 100 nanometers. So 100 nanometers, one band, 10 band, 1,000 nanometers as a total occupation. This makes sense. It matches the common perception that you have 3 bands in the visible range, because if you remember, the visible range is from roughly 400 nanometers to 700 nanometers, 0.4 to 0.5 microns, and 3 bands fit into it, 4 to 5, 5 to 6, 6 to 7. This corresponds respectively to blue, green, and red. Okay, so that makes perfect sense. When you switch to, and then there's the infrared, et cetera, but when you switch to hyperspectral remote sensing, you shrink the size of the band by at least 1 order of magnitude, so it's 10 nanometers. So the visible range, just to take a known reference, the visible range jumps from 3 to 30 bands. Okay, it's obviously a large change, and it's obviously something that basically entices data from the visual perception, because your eyes cannot see 30 bands in the visual range. You can only see 3, red, green, and blue. Okay. So as a first consequence, when you move from multispectral to hyperspectral data, you have a lot of data, a lot of layers. Remember that we had the 3-dimension K, L, and J, and I, J, and K. And the 3rd dimension was the depth, the bands. Okay, with Sentinel-2, we have seen 13 bands. When you have an hyperspectral data set, you have tens or hundreds or even thousands of bands. Okay. So when you pull the drawer from the filing cabinet, it comes out, and then you pull again, and it comes out, and you find an extremely long string of numbers. Okay, which have a great advantage in physical terms, that you have a lot of steps here along the wavelength axis, so you can describe this, theoretically, you can describe this curve accurately, okay? Theoretically. So you would be very happy to have such data, because, for example, this is a simple comparison in terms of samples. If you have multispectral data, the response of a certain object is, okay, one sample here, one sample there, et cetera, and the rest is you have to guess. Okay. When you have hyperspectral data, then you draw the curve much more densely. And in fact, if you look at vegetation, which I presented to you as a very simple behavior with 2 bumps and 2 dips, right? At least in the near visible range. Well, when you describe it using hyperspectral data, it becomes much richer in information. So, for example, you can, just a quick example, you can distinguish between chlorophyll A and B. In multispectral data, you just see that there's a dip in red and a dip in blue. This is the result of chlorophyll absorption. But if you had more bands at your disposal, you could see the difference between the action of chlorophyll A, which is located here, and the action of chlorophyll B, which is located here. In multispectral data, you simply put them together into one dip, and you're completely blind to this distinction. You can even see beta carotene. Okay. you have to know where to watch, and you have to have the correct data, the correct device that can break down the spectral response up to this point. And if you look at the entire deployment of the spectral curve, you will see that there are a lot of other possible data items that you can see. This is particularly important in agriculture, which is the topic of our next lecture. If you can learn all these things about a plant, you're very well placed in terms of understanding what is happening to such plants. Now, this is the technical difference. Okay, so technically what you have to do is to build a hyperspectral sensor, which is basically a hardware capable of so finely distinguishing the wavelengths and sensing them one by one. On the one side, you have much richer information, but on the other side, you also have disadvantages because it's technically difficult to do, meaning implying that there are few sources. So there exist a few hyperspectral missions. One is the Italian Prisma. Some of you know of it because they have worked with such data. There's the German NMAP. I don't know of any Indian hyperspectral satellite. But in general, there are very few attempts because it is extremely difficult and expensive. Hyperspectral sensing is more common in, for example, UAV-based remote sensing. But in satellites, it's extremely challenging to make the same device operate in a space environment. But missions are coming up. Okay, so I wanted to talk about this topic because this is something that in the next few years will for sure be developed. Okay, so more spectral information generally comes at the expense of coarser spatial resolution, or worse signal-to ratio, meaning that getting denser sampling of the spectral response doesn't come for free in a technological sense. If you want to have denser spectral resolution, you generally have to pay in terms of coarser spatial resolution. There's a technical reason for that. Or worse signal-to-noise ratio, i.e. greater noise, greater disturbances. So the measurement that you're doing is less accurate than for multispectral. Okay, and you have all these three problems combined. If you think of it, you have plenty of multispectral data available. Not so for hyperspectral. Plus, the resolution is coarser, and the quality of data is lower. Plus, last but not least, too many bands may hamper information extraction. So let me point out what happens here. It's a so-called Hughes phenomenon, which I briefly mentioned during one of the lectures. But let me expand a little bit on it. This graph represents the accuracy of a classifier. Basically, in our case, it is a classification accuracy. You know what is classification accuracy. We have seen also during the lectures. When you have, and this is the number of bands or number of information items. So in our case, the number of bands that you provide about the object, the unknown object that you are observing. Okay, so you train a classifier, and mind you, by training, I'm not necessarily meaning that I'm using a deep learning, as we have seen a deep learning machine, as we have seen in the classification lecture. Training means just tuning the classifier. So you train the classifier, and then you operate the classifier on the test data, and on the vertical axis, you report the accuracy. And it's also surprising that if you increase the number of bands, you break down the information, the behavior, in our case, the spectral behavior, into more bands, you get more information because you have more insights on the same object. And so the classification accuracy increases. But what is somehow surprising is that it increases up to a certain point, and then it peaks and it starts going down, which seems paradoxical because you're adding more information about the same object, but the classifier is less and less effective in identifying it. Okay? So this is one big issue with hyperspectral data. This is in general a big issue with any type of description of an object that you provide in a correlated manner. What do I mean? What is the problem here? So what happens here that drags down the accuracy? Because it's not intuitive, because you're adding information, right? You're saying, you're giving one more bit of information, which agrees with previous ones, and which should describe better the object that you're looking at. But the classifier gets confused and it starts making mistakes. Why? So the problem is that the data that you're providing is correlated. You're providing more data, but you're providing little additional information. While at the same time, on the other hand, by adding more pieces of information, pieces of supposedly independent information, because you're facing the problem from a general perspective, you're generating a data space which is increasingly big. Okay, so this is one-dimensional data, two-dimensional data, three-dimensional, five-dimensional, 10, 20, 50-dimensional data. You take a data space where with a lot of axes. So the training data that you may have is increasingly smaller. The size of the training data gets increasingly smaller with respect to the size of the data space. So this makes the classification process less and less effective. This phenomenon is unlikely to happen when you work with few-dimensional data. So if you operate on multispectral data, most likely you will not stumble into it. Okay? So we didn't discuss that a lot because it's not a real issue if you limit your work to multispectral data, even more so if you work with images, okay? If you work with RGB images, then this is not your problem, okay? Because basically you're working here. So adding bands brings up the accuracy. But when you move to hyperspectral data, it is a problem. Okay, so you generally have a curve, okay, a sort of, this is called the curve of dimensionality. You have a curve which expresses the performance as a function of the dimensionality or the number of features that you're using to describe the object that you're trying to recognize. And be aware that this is not a problem only for remote sensing. It's a problem for any case in which you're trying to recognize something based on a certain set of supposedly independent descriptions. Okay. increasing the number of features leads you to a peak and then to a decrease. Multispectral remote sensing operates in this range. Hyperspectral remote sensing almost always operates in this range. So paradoxically, if you were to remove bands, so to go back to multispectral remote sensing, you would improve your performance, which is strange. So why should I care? Why should I bother gathering so many bands to then throw away some of them? Professor Lal, in his previous lecture, briefly touched on this. Okay, we'll make a connection on that. Okay, so as I said, multispectral data is here, hyperspectral data is here. Now, let me answer the question. First of all, why should I bother collecting so many bands to then throw away some of these bands? Let me ask you this question. Why do I bother spending a lot of money, a lot of resources on building these devices which are capable of generating so many bands, which, after all, represent a problem? Why? Right. That's the point. Because if you don't do so, if you use multispectral remote sensing, you're completely blind to some types of information. Remember the graph I showed you earlier, chlorophyll alpha and chlorophyll beta, chlorophyll A and B. How can you distinguish them using multispectral remote sensing? You can't. Okay. So technically, you're collecting this information. The problem is downstream. This data description is not suitable for extracting the information. But the information is there. Okay, you did collect it. Now the problem becomes how to take it out of the data. The problem is not the information being there. The information is there. The problem is how to read it. Okay, so the investment in creating this hardware actually can pay off if you know how to do it. So typically, what you need to do is to reduce the number of bands, but it doesn't mean that you're falling back to multispectral remote sensing. So in general, what you have to do is to move from many bands to either a selection of these bands, which is called feature selection, or to generate more synthetic bands which summarize the information that you are looking for. Does that make sense? So if you think of it, this makes sense because you know the information is there. It has been collected. You just have to somehow make the bandwagon less crowded by throwing off those who don't serve any purpose. So the idea is you don't know in advance where the information that you're looking for is sitting in these many bands. You just know that blindly you have collected it. You put everything into a basket, okay? More or less unknowingly. Now, the problem is, I know that if the basket is too full, I cannot get the information that I want. Now, your task is remove whatever is not needed and get to a point where only useful information is still in the basket. Does that make sense? And so you have two strategies for doing this. This is actually matching the basket example. You have 200 bands. You remove 190 of these bands, and you select only the 10 ones which will tell you exactly what you're searching for. In this way, you will have pulled down the number of features, and you will get the maximum performance. But it doesn't mean falling back to multispectral remote sensing, because there's a big technical difference. In the case of multispectral, you are averaging together a broad range of wavelengths. In the case of hyperspectral, few bands have few tiny fractions here and there on strategic placements where you take the measurements. Does that make sense? Okay, so are you with me? Okay, great. The other possible strategy is instead called feature extraction. It may happen that not a single band conveys exactly the information that you're searching for. It may be a combination of various bands. And so you use so-called feature extraction, which means basically combining, generally linearly combining together a number of bands which all together convey the information that you're searching. In other words, when you use hyperspectral data, you cannot simply mutuate the approach that you would use for multispectral data. So if you try and push hyperspectral data into a classifier to directly classify it by maximum likelihood classifier, for example, or even a deep learning classifier, because the situation is similar. You get results which not necessarily are good because of the problem that I discussed previously. When you work with hyperspectral data, you have basically two distinct problems. One is to extract a feature that are useful for your purpose, so feature space. So you move the data from the original setting to so-called feature space, which only which only stores the relevant part of the data, and then you proceed to the analysis, meaning you try to obtain the information that you need. Okay. Now let me see. Yes. That's I was about to get there, because one of the you can. Basically, there's a number of techniques that you can use for band selection. Some are so-called supervised and some are unsupervised. And obviously, one is band subset selection. So select physical bands that best approximate PCA, but well, anyway, selection. But one of these is the principal component analysis. So PCA, which we have discussed when I taught about transformations, is one of the means that is commonly used to do that. When you do principal component analysis, you take the hyperspectral data set and you bring to zero the mutual correlation between any two bands, and then the new bands, you build the matrix that makes zero the correlation, that transforms the space, making zero the mutual correlation between any two different bands, and you get the so-called PCA bands, which generally are show the real amount of independent bands that are there. Because as I didn't express it clearly, but one big issue when you have so many bands is that you're generating correlated information. Like if you take, for example, this is a benchmark data set, typical one. This has been in use for decades. If you take any two nearby bands, like this is 6 and 16. If you take nearby bands, there should be a graph here showing it. No, it's not there, unfortunately. But anyway, if you take two nearby bands, the scattergram will be very, very narrow. So they will be very much correlated. This means that by adding the next band, you will add a lot of data, but very little information. Because when you add correlated data, you're adding very little to what is already known. And so correlation is part of the problem, because correlation means adding data without adding information. So you want to remove correlation. And PCA does exactly that. It removes correlation. So when you do, for example, PCA on the Indian pines data set, you will notice, even visually, you can assess that. The Indian pines data set contains 220 bands, 220 bands. But when you do PCA, you get only 6, maybe 7 bands with a significant information content. Okay, I'm saying you can assess it visually. This is an RGB rendition of the original data set. So spatial information will help you assessing whether the image that you're looking at makes sense, so it contains information or not. And once you do PCA, you will recognize that there's significant content up to band 6, maybe still something in band 7, maybe, but I don't know, in band 8. So with the original data set, I was using 220 different bands to describe something that could be mostly fitted into just maybe 8 bands. Okay, because of correlation. If I use something like PCA, which exactly eliminates correlation, I can reduce significantly the number of bands while still conveying the same information. The disadvantage of this approach is that, as always in the case of PCA, you're basically untying the bands from their physical meaning. Because as far as you have a band in the original data set, you know to what wavelength that band corresponds. Okay, so you know that, for example, that band corresponds to the absorption line of chlorophyll A. But once you have done this, band 6 relates no more to any specific wavelength. So PCA is is in the domain of feature extraction. So the disadvantage of feature extraction is that since you're mixing up everything, you don't know anymore what physical phenomenon has determined this band. Whereas in feature selection, where you kill a number of bands and you retain only the most relevant ones, these relevant ones which survive, they are still linked to specific wavelength. Okay. Yeah. So I think that's.
Feature selection, we can also preserve all the bands. Like consecutively, I will address uncorrelated band in one together. Next, I will go for other bands which are uncorrelated, not the remaining. That way, I can preserve all the bands.
I think I don't follow you. You mean?
I'm selecting features.
But you're working on one problem or multiple problems?
From multiple spectra, I can preserve all the bands, right?
You can preserve them all, but if you process them all together, then you end up with the same problem.
No, I will not process them all together. I will choose the bands which are far uncorrelated. First set of study. Next
So you mean?
Mm-hmm. Choose 10 bands which are uncorrelated, then again 10 bands successively.
But then you do not process them all at a time in any case. So the point is, I see now what you mean, but why would you, I mean, if there exists an ideal set of bands for solving a certain problem, why would you want to keep the others as well? So the point here is you have this many bands. You know that they are too many. You know that you don't need them all for your problem, and you need to take just some of them. But once you have made your selection and you have solved the problem based on the data in that selection, why would you want to use the other bands?
I want to keep the information. That was the problem with hyperspectral.
No, you have kept the information because most of the info, or at least the information, it depends whether, this is, I didn't talk about this, but you have two possible approaches to this. So you have supervised and unsupervised techniques. So I described the unsupervised techniques, but you also have the supervised techniques, in which, just like for classification, remember there's supervised and unsupervised classification. In unsupervised classification, you have an automatic operation in which you don't provide any input. It just happens, okay? In supervised classification, you're telling the classifier what you want. Now, the situation here is similar. In unsupervised feature selection, you just have a standard approach to feature selection or feature combination, which is, for example, PCA, where you don't need to provide any input to PCA. You just run the PCA, and it works, and you get the new set of bands. And you have made the selection. There also exists a so-called supervised selection or supervised combination procedure in which you know what you're seeking, and you provide this input to the selection technique by saying, I want to retrieve this type of information from the data. So please make your selection in such a way that this information is highlighted, okay? Then the purpose of, in both cases, if the result is suitable for your purpose, you don't need to pick up the other bands again. If you find that the result is not satisfactory, which typically may happen with unsupervised techniques, because with unsupervised techniques, you're moving blindly. Just saying, okay, just shrink the information, shrink the data, conserving as much information as possible, and you may discover that it didn't work very well. So you may want to consider supervised. But in any case, once you get to a point where you have the right information, you have extracted it, why would you want to retrieve the other bands again? Unfortunately, in some sense, in hyperspectral remote sensing, you need to waste some data. You see what I mean? Since the sensor was not designed for your specific purpose. Okay, so you may even know that you're interested in this and that lambda, because that's where you can estimate the health status of vegetation, or that's where you can find whether this is really concrete or it just looks like. Something that you cannot do with multispectral. You need hyperspectral. Okay? Okay, these wavelengths will tell you whether this is concrete or something that looks like concrete. Okay, but when you ask for hyperspectral data on the area, the hyperspectral acquisition will not have acquired just the bands that serve your own purpose. Okay, the acquisition is an hyperspectral acquisition, so it will take a lot of bands. It will put out at the disposal of any customer, right? So each individual customer, each individual data user will have the problem, will face the problem of making the selection of the data which is relevant to them. Does that make sense? So you cannot shrink data acquisition because you don't know in advance what the user is going to do with that data. Once you have acquired everything, you find that it's simply too many. So for any one of you with a distinct problem, that particular set of data will be too many data. So every one of you will have to face the problem of, okay, how do I adapt? How do I shrink this data in a manner that it conveys exactly the information that I need without retaining useless data? And that's why all these feature reduction or feature selection methods have been developed. Okay, so it doesn't mean that the data is useless. It just means that it may be useless for your specific purpose in that case. Okay. Okay. Great. Now I think we can close the topic of hyperspectral remote sensing, unless you have any question on it. Yes.
Out of that, the 6 images were visible properly. The 2 bands that were used that contain maximum noise in them. So does that contain any information? That's why we are keeping that component, means that band 8. Why could not we reduce it to further 4 images? Because it is more visible as compared to, as we are selecting from 200 bands. So
if I understood correctly, you want to determine a criterion to decide where to cut. Well, it depends on the application. Unfortunately, there's no general criterion, because if I guided you to assess this visually, so it's particularly, this is not a good example, but this one could be. So if you look at this series of PCA bands, you can assess that up to band 6, for sure, there's a relevant amount of information still contained there. From band 7, well, I don't know. From band 8, probably not. But the problem is, in this case, this is for educational purposes. I am using visual assessment as a proxy for information content. But it's not a very good criterion. Okay, so in some sense, you hit the problem. Because the message that I'm passing here is, if you look at the image, you can see that the information content keeps decreasing from one band to the next. So the look, the way the image looks is worse and worse because the amount of information is decreasing progressively, and so the noise emerges. But actually, I am leveraging spatial information because after all, you're looking at spatial information, right? So you're looking at the image. In order to assess whether it makes sense to your eye or not, you're leveraging spatial information. You're looking at the shapes of the object contained in there, and as far as the shapes make sense, you say, okay, it does contain information. But actually, the information is not spatial. The information is radiometric. So the fact that this image is ugly, or that this image is ugly, doesn't mean that it contains zero information. This is my point. It's getting worse. It's getting worse according to a certain progression, which I don't know. I know there's a visual companion to this getting worse, which is the worsening of the spatial information as well. So I use spatial information to pass the message that this is getting worse. Okay? But it's not the same thing. To give you a practical idea, because I mean, I'm not just being negative about that. One thing you could look at is the value of the eigenvector which is associated with each of these bands. Because the value, this is an eigen, so PCA is basically the application of an eigenproblem. Generally, when you do PCA, you look at the result in terms of multi-band data, but you don't really look into the eigenvalues which are generated by the same process. Now, if you do look at the eigenvalues, you will find naturally that they are placed in decreasing order, but the velocity with which the values decrease will generally indicate how fast the information contained here is. It's a proxy. It's not an exact measure. But the speed with which the eigenvalues will decrease from one band to the next will indicate whether the next band is still conveying significant information or not. It's still up to you to decide what it means, but in some cases, it does make a difference because you really see that, okay, there's almost nothing here, so throw it away. And if you have no better strategy, you can still try with a brute force approach, like, okay, this result is unsatisfactory. Let's try and add one more PCA band. Rerun the process and see what happened. Did it improve or not? Okay, so I would do so. Okay. Okay. So now, do we still have some time? Not really. 10 minutes. Okay. Okay, because but we still have a lecture in the afternoon, right? Okay. Lab, yes, but the first part of the lab will be presentation. We'll just introduce the topic here, and then I will. Okay, so the topic of the this last lecture will be agricultural remote sensing, because I wanted to complete the visiting of the processing chain from generation of data to processing to information extraction, now to possible applications. And in terms of applications, I focused on agricultural remote sensing. I focused on agriculture because that's what I am currently mostly working on. So, now, let's skip this. Now, spaceborne remote sensing is not an extremely recent technology. As I mentioned at the beginning, we had the Landsat series, which started as early as 1972. The space agencies were for a long time the only actors in the field because these missions were so expensive that no individual company could afford this spending. But this was true until the end of the last century. But with the start of the current century, the situation started changing. Started changing with an increasing presence of private companies. Why? Because oh, sorry, I lost slide. Wow. Let alone, no problem. Okay, the situation started changing. I probably lost that slide. I don't know why. Anyway, the situation started changing for a number of reasons. Started changing because the space technology got cheaper, especially the so-called CubeSat concept came in, which was that of let's not design every individual space mission alone, but let's try and standardize, as it happened with other in types of industry. Anytime you standardize, you can save money because your design effort will be reused by others, and you will be able to reuse others' efforts. Okay, so the CubeSat was a concept born in 1997 at the University of Barcelona, jointly at the University of Barcelona and the University of Southern California, if I remember correctly. These were academicians. They put their minds together and they came up with this concept of saying, okay, let's establish some standard measures and some standard devices that can be possibly used for a space mission. And let's publish this standard and see if the industry will respond. And this happened. So they basically started of the designing procedures, and devices were designed that could be used on multiple missions. Okay, and especially the focus was on the reuse of standard devices rather than devices that were off-the-shelf devices, rather than devices that were designed specifically for space, or space applications. And so the space industry took up, including on the Earth observation sector. And on the other hand, as I mentioned, there was the transition towards open data that favored. We have seen the Copernicus mission, but there are also other initiatives towards open data, which led to basically a flood of data available for free or for a moderate cost. What you see here is the graph of how much data was downloaded from the Copernicus portal in the years between 2015 and 2020. And you see the growth of, substantial growth of data that was observed from that point on. So to mean that the abundance of data that has been made available has favored the growth of applications based on it. And so this applied also to agriculture, where, and then this last couple of slides, and then I will close. The science of using remotely sensed data in agriculture started early in the 70s, even before the Landsat series started. Even before the Landsat series started, papers were published which foresaw what use could be made of these data in agriculture. Okay, so we're not talking about yesterday. This is something that has been going on for decades. But the problem was that lack of data and cost did not permit the development of operational systems. So the science was there, but the data was not sufficient. Data was too scarce and too costly, and did not permit the development of real applications. Now, why did I told you about the growth of data? For this reason. Because we are now at a point where we have the applications conceived and described and the science behind them, and we have data coming up with prices that are accessible. Okay, so now we can start working on remote sensing in agricultural context. The graphs that you see here represent the number of papers that are published with subjects in agriculture, broken down by type of platform. And you see satellites are generally the most widely used type of platform, and broken down also by type of data collected. And you see in this case, it's more evenly distributed. Okay, then I think I will stop here. This is just a brief introduction to the topic, and this afternoon I will develop it a little bit more, and then we'll have some practical exercises. Okay, thank you. Thank you.
So just apart from the schedule, one most important lecture, because the Fabio and the Professor Shyamlal has covered a lot of things with from the basic to the machine learning and the application point of view, how we can deploy the AI and the deep model. Now the most important lecture, Professor Katpatal, Dean RNC from the VNIT is with us. He will discuss the different case studies and the different type of the projects in the remote sensing, what we had done in the VNIT and what we can do in future also. So just I introduce the Professor Katpatal is a Professor HAG at the VNIT Nagpur. He joined VNIT Nagpur in the 1993. After a brief stint at the National Environmental Engineering Research Institute Nagpur from the 1992 to 1993, his research interests are in the area of spatial analysis through remote sensing data, geographical information system. Professor Katpatal completed several research projects sponsored by the different external agencies like MHRD, DST, NARL, etc. He has been granted 6 patents, and he is passionate about the Earth system and the human interaction. Hence, his area of the research focus on the impact assessment using spatial analysis. He has also worked as the Dean during the 2005 to 2009, Associate Dean International Affairs 2017 to 19, Chairman Special Cell of the VNIT during 2024 to 17, Head of the Civil Engineering Department from 2021 to 24, He is currently Dean Research and Consultancy at the VNIT since January 2024. He has published 304 research papers in the international and national journals, conferences, and the several books and the book chapters. He has been invited to several international conferences as a speaker and a member of the jury, including in the International Symposium on the Environmental Management at Athens, Greece, International Conference on Environmental Engineering at USA, International Conference of the Hydroinformatics at Singapore, International Conference of the Solid Waste Management, Philadelphia, USA, and so many more. He believes in sharing scientific information and has delivered 343 invited and expert lectures at the various platforms related to the remote sensing at the geoscience. He is also the reviewer for the around 40 international journals, and based on his contribution, Dr. Katpatal has been granted 6 patents, while another 4 patents on remote sensing and GIS have been filed. Dr. Katpatal has completed more than 50 consultancies in the area of remote sensing, GIS application to the several organizations. He has been awarded several awards and the best paper prizes for his contribution. He has also the membership of the various professional societies, fellow, life member of Indian Society of the Remote Sensing, Interwater Works Association, Interwater Resources Society, Indian Geological Congress, Indian Society for the Technical Education, the Indian Society of the Hydraulics, Indian Institute of Engineers, Maharashtra, Academy of Science, Mining Engineers Society, European Association of the Geophysicists and Engineers 2013 to 14. He has organized 7 international conferences, national conferences, and training programs. And Dr. Katpatal believes that Earth system and its sustainability is most important for the mankind. He very much likes teaching and the interaction with his students. So I warm welcome Sir for this GIAN course.
So thank you, Deep. Thank you very much. Dr. Fabio, the guest faculty for this program. Actually, he is the main person, and he must have taken to a journey how remote sensing and satellite data can be utilized for different applications to enhance the quality of life of the human being. This is a technology which changes everything. All the countries which have adopted this technology have been benefited immensely. Now today I am here just to share few case studies which have been done by my students. I have been very lucky that I always got good students actually. So some teachers are known by their own work and some teachers are known by the very good work done by their students. I have been very lucky that I got many of them actually, plenty of them. I got almost 29 students in PhD and 104 students in MTech projects. So I was very lucky. And the work which have been done by even the BTech students at the project level in the final year project, very small work here and there using the satellite data for monitoring and something. I think every information which has been extracted by somebody is very important because that important is required very badly some places. Okay. Now ultimate objective of technology application is to change quality of life. I am actually fan of the earth system and the natural system which actually always challenges our activities, which challenges our endeavors, technology, and this is the only area which changes so fast that we cannot, I feel that we cannot tame it by our artificial intelligence because it's a natural system which works in a very different manner. Okay, and we are trying to put artificial intelligence